This video, we're going to prove the following theorem. Assume that P and Q are distinct primes, distinct odd primes. That is, they're odd, but they're not the same. They're distinct, such that P minus 1 divides Q minus 1. Okay, that's like what's given. That's what we assume in this problem. If the GCD of P, Q, and A is 1, then A to the Q minus 1 is congruent to 1 mod P, Q. If you like seeing mathematical proofs, then you should consider subscribing to my channel, as that's all we do here. Okay, how about we get right into the problem? This statement here, the GCD of P and Q, PQ and A being 1, since P and Q have no common factors, they're prime, they have no common factors, and since the GCD is 1, that means that P, Q, and A have no common factors. But that actually implies, think about it, that the GCD of P and A is equal to the GCD of Q and A, which is 1. Okay. And we also know that the GCD of P and Q, since they're both prime, is also 1. So let's hold on to that. And that all came from this. We were given this, it implies that, which is equal to this, and that's always true if P and Q are distinct primes, whether they're odd or not. Okay, now we're also allowed to assume that. What does that mean? P minus 1, divides Q minus 1. By definition, that means Q minus 1 is a multiple, say M times P minus 1. It's a multiple of P minus 1. Okay. Now, where are we? From right here, okay, from the GCD of Q and A being 1, that implies that Q does not divide A. And Q is prime. Well, Fermat's little theorem will tell you that A to the Q minus 1 is congruent to 1 mod Q. That's from Fermat's last little theorem. Now, we are told, we came up with this right here. Okay, so A to the Q minus 1 is the same as A to the M times P minus 1, times P minus 1, which is A to the M to the P minus 1. Now, let's make a comment on this. That implies that P does not divide A. P and A have no common factors other than 1. That means that P does not divide A to the M. So A to the M is one number. Think of it as B. If B to the P minus 1 and P doesn't divide B, that implies that, this, by Fermat's little theorem, this is our A to the M mod P. Okay, but this here is the same No. I mean, that's true too, but I should say 1. 1 to the 1 mod p. That is what Fermat's little theorem says. Well, let me just let me rewrite this a to, without all the middle stuff. A to the q minus 1 is congruent to 1 mod p. Let's call that statement 1. How about statement 2? And this statement right here, how about statement 1? Well, 1 and 2. Well, let's see. Statement 1 implies that q divides a to the q minus 1 minus 1. And statement 2 implies that a to the q minus 1, p divides that. Okay. Now, here's the nice part. Let me just clean that up a little bit. Q and P, they have no common factors. They have no common factors. So if they both divide the same thing, that implies that their product divides the same thing. Okay. Now, for example, if you have 2 times 3, it is possible that 2 goes into, in this case, 6, and 3 goes into the 3. You know, maybe I could have used a larger number. 2 goes into 12 6 times, and 3 goes into 6 2 times. That's not going to happen with their prime, because if you have a prime, if you have a product of primes, you're not going to have, you know what, maybe that wasn't the best example. If you have 2 times 4 into 8, 2 goes into 8, how about 4? 2 goes into 4, and 4 goes into 4. But I'm done. This 2 doesn't go in. And the reason is, these 2 had common factors. P is not P is not composite. This is not going to happen. Think about why. Look at examples. Think. Okay. This statement implies that a to the q minus 1, this is congruent to that mod p. Mod pq. And this is exactly what we wanted to show. That's exactly what I wanted to show, and I did. That completes this proof. Subscribe to my channel. Leave a comment. See you guys in the next video. Watch and learn.